Of simulation theory often point to video games as a way to explain, if not prove, that our reality is artificial. In a video game, the only data that is rendered is what the player sees or interacts with. If you're playing a video game and there's a car or building a mile away, that entire object isn't rendered. The game engine only renders the bare minimum of information to make the object look real. A distant building is rendered as just a few pixels, not that complicated. As you get closer, the engine renders more details, but still, it's just a facade. The engine doesn't bother calculating what's inside the building until you actually go in. The game engine always knows how much data to send you and doesn't bother with anything else. If we live in a simulation, it would make sense that our reality is rendered the same way. And we could test this.
Wait, what do you mean we can test this?
Specifically, we can use the double slit experiment. Here's how it goes. If we fire particles in a straight line at a screen, after passing through a single slit, we would expect to see this clumping pattern on the screen. If we try this with a wave, we expect to see a pattern like this, where particles are most dense in the middle of the screen but radiate outward, similar to the clumping pattern. When we add a second slit, it starts to get fun. When the waves pass through the double slit, each slit creates its own wave. When those waves intersect, they cancel each other out. That creates a pattern like this. It's called an interference pattern. So, particles passing through two slits create clumping patterns. Waves through two slits creates an interference pattern. Make sense?
Yeah, I'm with you.
Good. If we fire electrons through the slit, we see the clumping pattern as expected. An electron has mass, so it's a tiny bit of matter. So if we fire electrons through two slits, we should see two clumps. But we don't. We see the wave interference pattern. This shouldn't be happening. What's going on here? For years, scientists assumed that the electrons were colliding with each other, causing the wave pattern. But in the 60s, the experiment was modified so that only one electron at a time was fired through the slits. There was no way the electrons could interact with each other, yet we still see an interference pattern. Scientists wanted to see what was causing this, so they added a detector to observe electrons as they pass through the slits. That's when things go from weird to paranormal. As soon as the detectors were installed, the interference pattern went away and the clumping pattern returned. Take the detectors away and the wave interference pattern is back.
But that's a different result to what we had earlier. So here's the last bit of sneakiness that we can play with atoms. Surely now, we're going to get to grips with it. Leave the detector there, but just very quietly go and unplug it. Don't let the atoms know that you're not spying on them. Run the experiment again. Now, if you can explain this using common sense and logic, do let me know, because there's a Nobel Prize for you.
It's as if the particles are aware they're being observed. Then physicist John Wheeler had an idea. He called it the delayed choice experiment. How it works is, photons are projected through the double slit, but the detector is not activated until after they pass through the slit, but before they impact the screen. Photons were emitted as waves, passed through the slits as waves, but when the waves were observed before hitting the screen, they suddenly behaved like particles again. Still don't think there's an intelligence at work? Well, what Wheeler's experiment showed is that even though the electrons started as waves but behaved like particles after being observed, at the moment the decision to observe them was made, the electrons recorded themselves as having passed through the slits as particles. The electrons changed their state by going back in time.
I personally find that I gravitate more towards the information theoretic point of view and believing that the universe that I exist in is a very good, high-quality simulation.
Now, this experiment is happening on a table in a lab, a very short distance. So what happens when we observe light coming from vast distances, like, say, a galaxy 100 million light years away? If light from a distant galaxy is projected through the double slit, it creates the wave interference pattern. But if we push those photons through a measuring apparatus to observe them, the wave again collapses all the way back to its source. This is called retrocausality. Simply by choosing to observe the photons this way, they reach back through time 100 million years and alter their state on the other side of the galaxy. But like a video game engine, it only does this if we're looking. Even though our universe is full of galaxies, those galaxies may not actually be there. If we're living in a simulation, then stars and galaxies could simply be projections, and only when we get up close will those projections become more detailed. This is an excellent way to save computational resources. And because we're stuck with the hard limit of the speed of light, getting to far-off places is really difficult. Limiting the speed of light is a useful rule to have in place. Quantum mechanics like the double slit experiment and quantum entanglement only make sense if there's a program at work, because only the program can ignore the laws of physics.